My name is Giacomo, and I did my project with Public Health England, Department of Health Executive Agency, which, among other things, runs NCROS, the National Cancer Registry. So, cancer is the most common cause of death in the UK, with around 28% of all deaths in 2016. Biomedical research is making a lot of advances in terms of knowledge of cancer biology, improvement on prevention and efficacy of treatment. But there is still one problem that defies all the efforts, and this is the problem of recurrence. So recurrence, broadly speaking, is when cancer comes back after treatment. There is no clear-cut definition of it, and there are many causes for it. So, as a result, it's not possible to predict whether a patient will have a recurrence or not. The increasing amount of data collected by NCROS makes it a perfect problem for machine learning. So the goal of my project was to find indicators of cancer recurrence, that is, find features that might be linked to a patient having a higher probability of getting a recurrence. And to this end, I was given a data set of more than 7 million events, clinical events, more than 200,000 patients, and more than 8,000 features. Examples of events were chemotherapy and radiotherapy sessions, accident and emergency visits, checkups, and so on. Examples of features were the types of drugs used in chemotherapy and details about diagnostic imaging, checkups, and so on. So, to find a pattern in a patient pathway data that is linked to a recurrence, the first thing to try might be to give the whole dataset to an algorithm and see what comes out of it. But the answer is not much, because patient histories are very noisy. They include events that are not linked to cancer, like accident and emergency, for instance. And moreover, recurrences are hard to assess. That means that even a clinician with all the medical records of a patient might have difficulties in deciding whether this patient got a recurrence or not. So I had to resort to a more tailored approach. Events, even if they are labeled by a patient ID, cannot just be given to an out-of-the-box model to get some results, because the out-of-the-box model cannot see relationships between events, in particular the temporal relationship, which is key in this problem. So in the end, I used time gaps between key events to construct a gap distribution for each patient, and with this I produced a collection of gap distributions, which I gave to a clustering algorithm to produce clusters of patients. So to visualize these clusters, I used TSNE, which is an algorithm that takes a high-dimensional data set and produces a two-dimensional version of it, just to visualize it on screen. So this is an example of the results that I got. Every dot is a patient, and they all gather together into clusters depending on their gap distribution. So I highlighted some of them because they are those with the longer gaps, and most likely these are linked with recurrences. So this information is getting passed to clinicians to get some medical feedback on these findings. Moreover, we can overlay some patient features on top of the clusters to see whether some patient characteristics are linked to the gap distribution of the clusters, and in turn, hopefully, to recurrences as well. So, for instance, in these bars are telling us that stage 1 and 2 lung cancer patients are more linked to long gaps rather than stage 4. And in conclusion, I extracted some valuable information from a very large and complex dataset with the aim of identifying patients who have high risk of recurrence. And this, with the help of clinicians, could lead to more personalized treatments, enhanced screening tests, and in the end, saving more lives. Thank you.